Hello to all. The topic of our video today pertains to recent advancements made by astronomers in observing the nearby exoplanet WASP 107b through the James Webb Space Telescope. By examining the planet's atmosphere, they found significant quantities of water vapor and sulfur dioxide, as well as an unexpected presence of silicate sand clouds. These clouds were found deep within the planet's fluffy atmosphere, which is in constant motion, exhibiting a highly active transport of material. Let us commence with our discussion. The James Webb Space Telescope has successfully detected several compounds in the atmosphere of a neighboring exoplanet. These compounds include water vapor, sulfur dioxide, and sand clouds, which have been identified through careful analysis of the exoplanet's atmospheric composition. The Institute of Astronomy, KU Leuven, was one of the co-leaders of a group of European astronomers who examined the atmosphere of the nearby exoplanet WASP 107b using the James Webb Space Telescope's latest observations. In their research, they delved deep into the planet's fluffy atmosphere and found water vapor, sulfur dioxide, and even silicate sand clouds. These particles exist within an active atmosphere which experiences robust movement of material. Scientists across the globe are utilizing the advanced capabilities of the mid-infrared instrument MIRI on the James Webb Space Telescope, JWST, to conduct revolutionary observations of exoplanets, which are planets that orbit stars other than our Sun. One of these captivating worlds is WASP 107b, a distinctive gaseous exoplanet that circles a star that is slightly cooler and less massive than our Sun. Although the mass of the planet is comparable to that of Neptune, it is significantly larger in size, almost approaching the size of Jupiter. This feature results in WASP 107b being relatively fluffy in comparison to the gas giants in our solar system. The fluffiness of this exoplanet allows astronomers to delve into its atmosphere to a depth that is approximately 50 times greater than what they can achieve for Jupiter, which is a giant planet in our own solar system. The European astronomers' team maximized the exceptional sponginess of this exoplanet to their advantage, which enabled them to probe its atmospheric depths. This allowed them to gain insight into the intricate chemical makeup of the exoplanet's atmosphere. The rationale behind this is quite simple. The signals, also known as spectral features, are more conspicuous in a sparse atmosphere than in a denser one. According to their recently published study in Nature, they discovered the existence of water vapor, sulfur dioxide, SO2, and silicate clouds. However, it is noteworthy that there is an absence of methane, CH4, the greenhouse gas. The discoveries made in relation to this captivating exoplanet offer invaluable insights into its dynamics and chemistry. The absence of methane, for instance, indicates that the interior of the planet could be warm, giving us a tantalizing hint of the movement of heat energy within its atmosphere. In a major surprise, sulfur dioxide, best known for the odor of burnt matches, was discovered. Previous models had predicted its absence, but new climate models of WASP 107b's atmosphere suggest that its fluffiness is the key to accommodating the formation of sulfur dioxide. Despite its host star emitting a relatively small fraction of high-energy photons due to its cooler nature, the fluffy nature of the planet allows these photons to penetrate deeply into its atmosphere, thus enabling the necessary chemical reactions for the creation of sulfur dioxide. The observations made by astronomers go beyond what has already been mentioned. They have noticed that the spectral characteristics of sulfur dioxide and water vapor are considerably reduced when compared to what they would be if there were no clouds present. High-altitude clouds partially obscure the presence of these substances in the atmosphere. While clouds have been inferred on other exoplanets, this is the first time that astronomers have been able to accurately identify the chemical composition of these clouds. In this specific case, the clouds are composed of small silicate particles, a recognizable material for humans that is found in many regions of the world and is the primary component of sand. Professor Leon Dacian from KU Leuven, the lead author, states that JWST is transforming the process of characterizing exoplanets, granting incomparable knowledge at an incredible rate. The revelation of sand, water, and sulfur dioxide clouds on a gaseous exoplanet by JWST's MIRI instrument is a significant turning point. This discovery modifies the way we comprehend the creation and transformation of planets, while also illuminating previously unknown aspects of our own solar system. In comparison to Earth's atmosphere, where water solidifies at low temperatures, gaseous planets have temperatures that reach up to 1000 degrees Celsius, which can cause silicate particles to solidify into clouds. The traditional models indicate that these clouds should form deeper within the atmosphere of WASP 107b, which has an outer temperature of approximately 500 degrees Celsius. This is perplexing since the temperatures there are substantially higher. Furthermore, sand clouds that form in the upper atmosphere eventually dissipate. The question then arises, how do these sand clouds persist at high altitudes? Dr. Michiel Min, the lead author of the study, states that the presence of sand clouds in the upper atmosphere is an indication that the sand droplets of the sand rain must evaporate in hotter, deeper layers. This leads to the creation of silicate vapor that is efficiently transported back up, where it recondenses to recreate silicate clouds. The cycle of sublimation and condensation through vertical transport is similar to the water vapor and cloud cycle on Earth, but with sand droplets instead. This process is responsible for the sustained existence of sand clouds in the atmosphere of WASP 107b. The groundbreaking research not only illuminates the enigmatic realm of WASP 107b, but also expands the limits of our knowledge regarding exoplanetary atmospheres. It is a noteworthy accomplishment in the exploration of exoplanets, exposing the complex interdependence between weather patterns and chemical components on these remote planets. Lead author Dr. Akreen Dirick at CEA Paris exclaims, "With JWST, the opportunity to perform a thorough analysis of the atmosphere of an exoplanet that has no parallel in our solar system becomes available, revealing uncharted territories." The creation and construction of the MIRI instrument was significantly aided by the Belgian Federal Science Policy Office BELSPO through the ESA Prodex program. This is largely due to the contributions made by key Belgian scientists and engineers from various institutions, including Thales Alenia Space in Charleroi, the Centre Spatial de Liège, CSL, and OIP Sensor Systems in Oudenaarde. Additionally, the Institute of Astronomy at KU Leuven played a crucial role in the development process, specifically in conducting extensive testing of the MIRI instrument. This testing was done in specialized chambers that simulated the conditions of space, both in laboratories located in the United Kingdom and at the NASA Goddard and Johnson Space Centers. Dr. Bart van den Busch, an instrument specialist from KU Leuven, expresses satisfaction in seeing the MIRI instrument, a project that he and colleagues from the United States and Europe have spent almost 2 decades constructing and evaluating, successfully uncover the mysteries of the atmosphere of a captivating exoplanet. Dr. Jeroen Bouwman, from the Max Planck Institute for Astronomy in Germany, states that the culmination of several separate analyses of JWST observations has resulted in this study. The years of effort invested in the creation of the MIRI instrument and the development of calibration and analysis tools for the observational data obtained with MIRI have contributed to this achievement. These observations were taken as a component of the Guaranteed Time Observation Program 1280. The James Webb Space Telescope is the leading astronomical observatory for space science worldwide. Its primary goal is to unravel the unknowns of our solar system, expanding its scope to examine alien worlds orbiting other stars and seeking answers about the inexplicable structures and origins of the universe, as well as our position in it. This international program is spearheaded by NASA, in conjunction with its partners, the European Space Agency, ESA, and the Canadian Space Agency. The consortium of European astronomers is made up of a total of 46 scientists, hailing from 29 different research institutions and spanning 12 distinct nations. Among the members of this team is a group of researchers from KU Leuven, including Lien Dessin, Thomas Konings, Bart van den Busch, Ioannis Argyriou and Linus Heinke. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.